Okay, for this next example, we are going to take each of the following statements and explain whether we think the variables will have positive association, negative association, or no association. The first one is years of education and annual salary. Generally speaking, I think we would all agree that this is positive. And that's because the longer you go to school, the more money you should make. What about interest rates on car loans and the number of cars sold? If the interest rates are higher, meaning the loan costs you more money to pay back, do you think people will sell more or less cars? And the answer here is this one has negative association, because the higher the interest rates, the fewer cars we sell. What about head circumference and GPA? So if we took a tape measure and measured around all of our heads, do you think that a higher head circumference a larger head circumference means we have a higher GPA or a lower GPA, or do you think that there's no association whatsoever? And for this one, I would say there is no association. The size of your head should have no bearing on your GPA. So all of this is an introduction, and we were just eyeballing the graphs and using data. Now we're going to, using common sense to decide whether data would have what type of correlation. Now let's start talking about how we do this formally, meaning using statistics to do it. Let's start by talking about something called the linear correlation coefficient. So it's dangerous to use only scattergrams to determine if two variables are linear related, because using different scales on graphs could possibly result in incorrect conclusions. Therefore, numerical summaries of bivariate data should be used in addition to the graphs to describe any relation that exists between the two variables. This brings us to the linear correlation coefficient. The linear correlation coefficient, and I realize that's a mouthful, or it's also called the Pearson product moment correlation coefficient, which is even more of a mouthful, is a measure of the strength and direction of the linear, and it's very important, this only works for linear relations, between two quantitative variables. The Greek letter rho, it looks like a slightly altered P, represents the population correlation coefficient, and R represents the sample correlation coefficient. Here is the formula for the linear correlation, to find the sample linear correlation coefficient. You take each data value, or the x of each data value, subtract the mean of the x's, divide by the standard deviation of the x's, and multiply that by the corresponding y data value minus its mean divided by its standard deviation, all over the sample size minus 1. Oh yeah, and we have to add all of those up in the numerator. Don't worry about that formula. That's just there to show you what happens underneath. Fortunately, we have technology. So let's talk about the properties of this linear correlation coefficient, because these things are important. The linear correlation coefficient is always between -1 and +1 inclusive. That means it can equal -1, and it can equal +1, and it can be any number in between. So if we wrote that as an inequality, we would write it like this. The second property is if R equals -1, or if R equals +1, which we can write those two statements like this: R equals ±1. So this statement is the same as both of these. It's just shorthand math for so we don't have to write two separate things. So if the correlation coefficient is 1 or -1, then a perfect, let me try that again, because I am jumping the gun here. So if it equals +1, then it's a perfect positive linear relation. I was trying to combine these into one. I forgot what I wrote in the notes. If the correlation coefficient is a -1, then it's a perfect negative linear relation. The closer R is to 1, the stronger the evidence of positive association between the two variables. And the closer R is to -1, the stronger the evidence of negative association between the two variables. If R is close to 0, then little or no evidence exists of a linear relation between the two variables. It's important to note here that R being close to 0 only implies there is no linear relation. But there could be a nonlinear relation. The seventh property is that the linear correlation coefficient is a unitless measure of association. And by units, we mean minutes, hours, feet, some type of measurement unit. The linear correlation coefficient does not have any units. So, the good thing about that is that the units of measurement for X and Y have absolutely no role in interpreting R. The correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of data could affect the value of the linear correlation coefficient. Remember, resistant means that extreme values do not affect it. So not resistant means that unusual values or values that are extreme or don't follow the pattern can affect it. So we'll talk about some more in the next video.